Hi everyone. So in this video, I'm going to go over the first, I think it's 8 questions, 7 questions of the set. And then starting with question 8, these are kind of like the homework to do individually. So that's basically what we're going to do. So this is all review from General Chemistry 1. It says how many moles of FeS2 are in 632 grams of iron pyrite, which is FeS2. So the first thing we need to do is we need to look up the molar mass of FeS2. So you could just Google molar mass FeS2 and you can get it, or you could just Fe plus 2 S's on the periodic table, whatever is easier for you. It turns out that the molar mass is 119.98 grams according to Google. So here we're starting with our 632 grams of FeS2, which we want to convert it to moles. So we know the molar mass. We know that 1 mole is 119.98 grams. Well, since we want grams to cancel, we put the 119.98 grams of FeS2 on the bottom, and on top, 1 mole of FeS2. And when we do that math, multiply by the top, divide by the bottom, what we find is there's 5.27 moles of FeS2. The second question says, how much sulfur dioxide in grams can be formed by reacting 15 grams of carbon disulfide, this one, with 35 grams of oxygen, this one, and whoever wrote this, which was probably me, forgot to put the states of matter. These are all gases. This one depends on the temperature. So we have 15 grams of carbon disulfide and 35 grams of oxygen, and we're asked for how much sulfur dioxide we can form, and we want to know the limiting reagent. So in this case, we have a mass of both of our reactants. So essentially what we need to do is we need to figure out the limiting reagent, or what's going to run out first. So I'm going to start with CS2 because it came first, but we have grams of CS2, and then we want to convert that to moles of CS2, and then to moles of SO2, because it asks us how much sulfur dioxide can be formed, and it asks us for that in grams. So finally to grams of SO2. To do that, we're going to need some molar masses. But first, we're going to need the amount of CS2 that we have. So starting with 15.00 grams of CS2 times, we want to convert it to moles. The molar mass of CS2 happens to be 76. So we want the 76, happens to be 76.13 grams of CS2 on the bottom, and the 1 mole of CS2 on the top, just like in the previous question. We now need to go from moles of CS2 to moles of SO2. To go from moles of one thing to moles of another, we always use the balanced chemical equation. In this case, we want CS2 to cancel out, so we put the 1 mole of CS2 on the bottom, and on the top, the 2 moles of SO2. Then we want to convert to grams of SO2 using the molar mass of SO2, which happens to be 64.07. In this case, we want moles to cancel out, so we put the 1 mole of SO2 on the bottom and the 64.07, the molar mass, grams of SO2 on the top. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. Repeat until you get to the end, and we get 25.25 grams of SO2 when we use all of our CS2. Well, now we need to see if this runs out first. And the best way to see if this runs out first is figure out how much SO2 we can make with all of our O2. So in this case, we want to convert from grams of O2 to moles of O2 to moles of SO2. Okay, so now we're going from O2 to SO2. And then the last step's the same. We want to convert those moles of SO2 to see how many grams we're going to get. So in this case, we want to start with our 35.00 grams of O2. Now, it's really important to remember that oxygen is O2. I mean, it says it here, but we need to double the molar mass. So it's not 16 that we want to put down here. It's 32.00 grams of O2 on the bottom. And on top, 1 mole of O2. We now want to convert from moles of O2 to moles of SO2. Again, moles of one thing to moles of another, balanced chemical equation. So the balanced chemical equation tells us that for every 3 O2, we make 2 SO2. We want O2 to cancel out, so we put our 3 moles of O2 on the bottom and our 2 moles of SO2 on the top. We now want to convert to grams of SO2. If you'll notice, in both cases, the last step is moles of SO2 to grams of SO2, moles of SO2 to grams of SO2. So it's the same conversion, use the same conversion factor. 1 mole of SO2 on the bottom, just like above, and 64.07 grams of SO2 on the top, just like above. And when we do this time, when we do the math, multiply by the top, divide by the bottom all the way through, we get 46.72 grams of SO2. All right, so we did a whole bunch of math, and we got some numbers. What do these numbers mean? Well, these numbers mean that if we use all 15 grams of CS2, we'll make 25 grams of SO2. If we use all 35 grams of O2, we'll make 46.72 grams of SO2. But here's the problem. We don't have enough CS2 to make all these grams of SO2. Why? Because if we use all of it, we can only make 25 grams. So this, the lower number, is called the theoretical yield. Okay, because we make this much, and we're now out of CS2, so we can't make any more SO2. We can't make 46 grams, because after we make 25 grams, we don't have one of our starting materials. So this is the theoretical yield. CS2, and I'm just going to abbreviate LR, is our limiting reagent. So this is our limiting reagent because it limits how much SO2 we can make, because we make less if we use all of this. And of course, once we use all of this, we can't make more than 25.25 grams because we have none of this left. So this is a limiting reagent problem from General Chemistry 1. Question 3 says, calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate, Na2SO4, in enough water to form 125 milliliters of solution. So there's multiple ways to do this, but one thing that we need to know is that molarity, which is a unit of concentration, which is used a lot in General Chemistry 2, so we need to remind ourselves what it is moles of solute divided by liters of solution. Okay, and one way to solve this problem is to convert this grams to moles using the molar mass of sodium sulfate, stick it in here. Convert these milliliters to liters, divide by 1,000, and stick 0.125 in here, and then do this calculation. Another way to do this is to do something that looks more like dimensional analysis, which is how I'm going to do it, but it doesn't really matter. So in my case, I'm going to take grams of Na2SO4. I'm going to convert it to moles of Na2SO4. And now this is not a conversion, because now I'm forming a new unit, not just converting one unit to another, but I'm going to take those moles of Na2SO4 and divide it by liters of solution. And moles divided by liter gives me my molarity, which is big M, the abbreviation for molarity. So in this case, I'm going to start with 23.4 grams of Na2SO4 times, I want to put the molar mass of Na2SO4 on the bottom, which I looked up on Google, and it's 142.04 grams of Na2SO4 on the bottom. On top, 1 mole of Na2SO4. Now, I want to divide by liters. In dimensional analysis, to divide, we put a unitless 1 on the top, because that just moves this unit over. This will be moles of Na2SO4 as a unit. And then, I want to put the volume in liters on the bottom, so then I'll have moles per liter, which is my molarity. In this case, I can't put in 125 milliliters. I have to put this in liters, divide that by 1,000, which is 0.125 liters. When I do all that math, I get 1.32 molar Na2SO4 solution. Question 4 says, how many milliliters of 3.5 molar sulfuric acid are needed to make 250 milliliters of 0.1 molar sulfuric acid? So this is a dilution question. We have a more concentrated acid, and we want to make it into a less concentrated acid. And we use this in the lab and in the lecture quite often in General Chemistry 2. So here we want to use C1, B1 equals C2, V2. Okay, so this is the initial concentration times the initial volume equals the final concentration times the final volume. In this case, the initial concentration is the more concentrated one, which is 3.5 molar. The initial volume of this 3.5 molar solution we need is how many milliliters. It's the variable. That's what it's asking us. So I'm just gonna leave that as V1. C2 is the final concentration. We want to turn this 3.5 molar sulfuric acid into 0.1 molar sulfuric acid. And it tells us that we want to make 250 milliliters of that sulfuric acid, the 0.1 molar. Note that I don't need to change this to liters. If I did, it wouldn't be wrong, but it's not necessary to do that because essentially we have a proportionality here. So multiply these two numbers together and divide by that one, and we find that V1 here equals 7.1 milliliters. So if we take 7.1 milliliters of this more concentrated acid and add it to, about 243 milliliters of water, we will end up with a 0.1 molar sulfuric acid solution. Number 5 says, what is the minimum number of grams of calcium hydroxide required to completely neutralize 25 milliliters of 0.1 molar nitric acid? So this is a tough question because we're not given the chemical reaction, this is the first and only one where that's the case. So in this case, we have an acid-base reaction. We have calcium hydroxide, which is a base, reacting with nitric acid, which is an acid. So we're going to take CaOH2 aqueous, and we're going to react it with HNO3 aqueous. And what we're going to form is a double displacement reaction. Ca goes with NO3, and H goes with OH, and HOH isn't written as HOH, it's written as H2O, or water, and that's what makes this an acid-base reaction. So calcium goes with nitrate. Calcium is in group 2A on the periodic table, so it's 2+. Nitrate is NO3-, it's one of those polyatomic ions that you should have memorized. We then cross the charges, although it's not necessarily to have it memorized here. So we cross this and we cross that. And what we find is that the formula of calcium nitrate is CaNO3 2. And that happens to be soluble in water. And then again, H goes with OH to form H2O liquid. So we've written the stable products of this reaction. We now need to balance it. If you notice here, we need 2 NO3s to make the calcium nitrate, so we need 2 HNO3s. We now have 2 H's and 2 OH's, which means we can form 2 HOH's, or 2 waters. Okay, so now we have the balanced chemical equation. Now it's not so different from previous questions that we've done. So let's reread it. It says, what is the minimum number of grams of calcium hydroxide required to completely neutralize 25 milliliters of 0.1 molar HNO3? So in this case, we want to go from volume of HNO3 to moles of HNO3. Then we can go to moles of CaOH2, and then finally to grams of CaOH2. Okay, so that is basically our goal. Now, if we look here, we're given the volume in liters, and we need this in milliliters. So we don't want to put in 25 milliliters. We want to put in 0.0250 liters of this HNO3 solution. So we need to divide that by 1,000. Now we want to convert it to moles. So we've, in several previous questions, converted grams to moles using the molar mass. To convert a volume of a solution to moles, we need to use the molarity. And this is 0.1 molar, which means it's 0.1 moles per 1 liter. In this case, we want to put the 1 liter of the HNO3 on the bottom and the 0.100 moles of HNO3 on the top, because we want liters to cancel and we want to be left with moles. We now need to convert from moles of HNO3 to moles of calcium hydroxide. To convert from moles of one thing to moles of another, we need the balanced chemical equation, which is why we wrote the balanced chemical equation. In this case, we have 2 moles of HNO3 on the bottom, and that's what we're trying to get rid of, and then 1 mole of CaOH2 on the top. That's what we're trying to end up with. Finally, we need to go from moles of calcium hydroxide to grams of calcium hydroxide, and we've done this in previous questions. We need the molar mass. So you can look this up on Google, and it's 74.09 grams of calcium hydroxide per mole. In this case, we want the 1 mole of the CaOH2 on the bottom, and the 74.09 grams of CaOH2 on the top. multiplied by the top, divided by the bottom, multiplied by the top, divided by the bottom, repeat to the end, and we find that this is 0.0926 grams of CaOH2, calcium hydroxide, sorry, it's off the screen, that is required in order to completely neutralize the 25 milliliters of this acid. It says, indicate each of the following that are soluble in hexane. Hexane is C6H14 and is non-polar. So in this case, what we're using is like dissolves like. And in like dissolves like, what is alike is polarity. So polar and ionic solutes are soluble in polar solvents. Water is the most famous polar solvent. Ionic solutes, like NaCl, are also soluble. K2O, although ionic, isn't really soluble in anything because oxides don't tend to be soluble. Maybe it's a tiny bit soluble. Okay? Non-polar solutes are soluble in non-polar solvents. So what's non-polar? Well, we could draw a Lewis structure and determine if something is polar or non-polar, and that's something you'll be doing in the early parts of Gen Chem 2. Or we can look for other hydrocarbons. So C10H8, which only contains carbon and hydrogen, is nonpolar just like hexane, because molecules that only contain carbon and hydrogen are nonpolar. So this molecule is going to be soluble in hexane, and these molecules are not. Number 7 says, draw the best Lewis structure for each of the following. So on this playlist, I'm also going to attach a video where I go over in great detail Lewis structures, and it's nearly an hour long, and it goes over the rules for drawing Lewis structures. But in this example, I'm not going to do that, okay? I'm just going to go over these relatively quickly. All right, so the first step to drawing Lewis structures is to count the valence electrons. So carbon's in group 4A, so it has 4. Oxygen is in group 6A on the periodic table, so it has 6, and there's 2 of them. So 4 plus 2 times 6, which is 12, 16 electrons. Step 2 of drawing Lewis structures is to put the least electronegative atom in the middle. If you remember your periodic table here, increasing electronegativity is in this direction, excluding the halogen. So fluorine's the most electronegative, oxygen's the second most electronegative, and carbon's about right there. So carbon is the least electronegative of these 2 atoms, so I'm going to put it in the middle, and I'm going to bond it to 2 of these oxygens. Now I'm going to put my 16 electrons. So 2, 4, 6, 8, 10, 12, 14, 16. So there's my 16 electrons having been placed. Now the last thing that I want to do, well not the last thing, but the second to last thing I want to do is fill the octets. So rule 3 is to fill the octets. So I've filled the octets of oxygens, but I have not filled the octet of carbon. And rule 3A is if you don't have any more electrons, so I've used all 16 electrons, so I don't want to just put more electrons like that, I need to make multiple bonds. And it turns out that I actually want to make 2 double bonds. And I'm going over this way more quickly than I would go over this if it was the first time somebody was seeing it. So if this doesn't make sense to you, I strongly recommend watching that other video. It's worth your time. It'll help you in Gen Chem. It'll help you in organic chemistry. And the more times you see it, the quicker you'll be at doing these things, and it'll help you out. All right, let's look at nitrate. We're going to do the same thing. Nitrogen's in 5A, so we have 5 plus 3 times 6 for the oxygens in 6A. And we have to add 1 extra because it's negatively charged overall, which gives us 24 electrons. I put nitrogen in the middle, and I bond it to 3 oxygens. And I know that if I put 8 electrons around each oxygen, 3/8 is 24, so I will have used all of my electrons. Now, what I want to do is, I want to essentially fill the octets. So I filled all the octets of the oxygen, and at the same time I've used 3/8, which is 24 electrons, but I haven't filled the octet of nitrogen. So I want to make another bond like this. Now I have nitrogen double bonded to an oxygen, like so, single bonded to an oxygen, like so, single bonded to an oxygen, like so. Now I want to calculate my formal charges. Well, oxygen wants 6 electrons around it, and this oxygen has 1, 2, 3, 4, 5, 6. It's neutral. This oxygen wants 6 electrons around it. It has 1, 2, 3, 4, 5, 6, 7. So this one is minus. This nitrogen wants 6 electrons around it and has 1, 2, 3, 4, 5, 6, 7. It is exactly the same as the other one, so it is also minus. The nitrogen is positively charged. It wants 5 electrons around it because it's in 5a on the periodic table, and it has 1, 2, 3, 4. Now, there's a lot going on with this. So, if you want to see a detailed explanation of how to find either of these, you will find them in the videos. This is the abbreviated quick version for someone where this is completely review. So please do see the other video if you would like more details, because I did a pretty poor job of explaining those, because it would take me half an hour to really explain it in great detail. Thanks for watching the video, and the rest of them are very similar to these.